So in the second half of today's lecture, we are going to discuss matrices. So what are matrices? So matrices are nothing but functions. They're linear functions. Their argument is a vector. So this is a matrix in a three-dimensional vector space. The argument is a vector, and the result is another vector. So you input a vector here, you're going to get a vector output. So if this is x, and this matrix is called T, then this is Tx. This is a linear operation because if I have y, this is Ty. If I have x plus y, then the result is independent of the order of the operation. I could multiply t by x plus y, or I can multiply t by x and multiply t by y and add the result. Because the result has this property, this is a linear operator. So let's just start from the simplest linear function. The simplest linear function is a function from R to R. This function takes any number and gives me another number, but basically multiplying a, which is a real number, by x. If a is not 0, then given any number, this is 0. If a is not 0, then given any number here, x, I'm going to get another number, ax. And given any number ax here, I can trace it back by dividing by a and get x. So this function, if a is not equal to 0, is actually invertible. Because I can go from one side to the other, or I can go back from one side to the other. I can have another linear function where every vector I'm going to give you one number to it. So simply saying f of x is equal to a number f11 and a number f12 multiplied by the first component plus that number multiplied by the second component. So given a vector x here, and notice that I can have a vector here f that I'm going to call, or vector here v. Let's meet out of the components f11 and f12. This operation from here to here is basically gives me f or v dot x. Because when I take the dot product between v and x, I'm multiplying f11 by x1, f12 by x2, I get a number here. Now obviously this operation is not invertible. Because if I have a number here 5, let's say this is equal to 5. If I have 5 here, there are many vectors here that when I multiply them by this, I will get also 5. So this operation is not invertible. It's still linear. This is a linear operation that's not invertible. It's a linear function. F is a linear function. It takes me from R2 to R, but it's not invertible. Here's another function that gives me R2 takes a vector in R2 and gives me another vector in R2. Such that this is B, and these vectors B and U, and I have any other vector X. The first component of the new vector is actually d dot x. So this is vector f of x. Let's call it y. This vector has two components. The first component is equal to v dot x. And the second component is equal to u dot x. And so for this operation to be invertible, which means for this operation I can go either way for every vector, for every x here, there is a y in R2 such that, and for every, that's not, we're going to cover invertibility in a second. Basically, for every vector here, for me to find a vector that is the reason y, or that's the pre-image of y, so for every y, for me to find an x that's the pre-image of y, these two vectors that form the linear map have to be linearly independent. U and V have to be linearly independent for me to be able to have this matrix, to have this relationship invertible, or this function invertible. Now for every linear function, from Rn to Rn, this linear function can be represented by a matrix. And this matrix will have the form made out of n vectors. Such that when I multiply this matrix by a vector, I'm taking the dot product between the first vector and the column vector to give me the first component of the new vector. So Tx, which is equal to all these vectors, will give me the first component of the new vector is basically the dot product between v1 and x. The second component is v2 dot x. The third component is v3 dot x. And so on, all the way up to vn dot x. That n new components, those n new components are obtained by taking the dot product of the rows vectors multiplied by x. Now the basic definition of a linear map, a linear map T between two vector spaces V and W is a function T from V to W such that any two vectors in V, any two real numbers, the order of the operation alpha x plus beta y multiplied by t is not really important. I can multiply alpha x plus beta y and the result multiplied by that t, or take alpha out and beta out, multiply t by x, multiply by alpha plus beta ty, I get the same result. Now, under this definition, is this a linear function or not? So let's try alpha x plus beta y. And let's try alpha f of x plus beta f of y. Alpha f of x will be alpha ax plus b. Beta f of y will be beta ay plus b. So is it a linear operation or not? It's not a linear operation. It's not a linear operator because these two are not equal. Of course, b is not equal to 0. Because if b is equal to 0, then they're equal. So this function, not any function, is a linear operator. A linear operator has to satisfy this problem. So, injectivity, surjectivity, and bijectivity is a very, it's a very important concept when you're dealing with linear algebra, because, as we said, the finite element analysis softwares know whether your structure is stable or not by realizing whether your matrix is invertible or not. And so we really need to understand these three concepts well. An injective function is a function that takes any two or any element in X and gives me a unique element in Y such that Y equal to X. An example? An injective map is a map that gives me a unique result. Students in 665, an ID number. For every student here, you have a unique ID number. So there's a map on bare tracks or in E-class that gives me your unique ID number. Now this map is not invertible. Why is it not invertible? Because when I look at the ID numbers in U of A and I try to come back, I might not find a student in 665 that corresponds to that ID number. this map is injective, but it's not invertible. So invertibility and injectivity are two different things. Injectivity means it's a unique, for every x, there's a unique y. The surjective function, so injective is also called one-to-one. The surjective function, or also called onto, if every point in y, I will find at least one in x such that t of x equal y. Which means I'm covering all the ID numbers. Example, for surjective map, which is onto. If I have students and gender, male, female, for every student here, they're either going to be male or female. And so this is surjective because I cover all my codomain. I cover all y. Every element in y, be it either male or female, I can find at least one that is a student in 665 that is either male or female. Now this is not an invertible because if I choose male, I cannot find only one. I can find a lot of them that are males, so this is not an invertible function. A surjective function is not necessarily invertible. Invertible means I can find a function the other way, or the opposite direction. Here, male, there's a lot of other possibilities for the inversion of this function. An invertible function is a function that is both injective and surjective. Only when for every element here, there is one unique element in y that's injectivity, and for every element in y, I can trace it back to an element in x, that's surjectivity. Once it's injective and surjective, then this function is invertible. One-to-one and onto. Function is invertible if it's both one-to-one and onto. So why is this important for our matrices? Because of the following. Any matrix, as we mentioned earlier, can be represented, or any linear map is represented by a linear set of vectors. by any n by n matrix can be represented by n vectors, or has n vectors. For this matrix to be invertible, then these vectors have to be linearly independent for a matrix to be invertible. The row vectors have to be linearly independent. And the following arguments are arguments are important to understand. If the determinant of m is 0, the determinant of m is a measure of whether these vectors are linearly dependent or not. If the determinant of m is 0, then the vectors associated with m are linearly dependent. If the vectors associated with m are linearly dependent, then m is not invertible. And what does it mean that m is not invertible? It means the following fact by which a software knows whether a structure is stable or not. If m is not invertible, it means the following. M takes vectors from here to here. Let's say from R2 to R2. It means that there's a vector here. There exists x in R2. X is not equal to 0. Yet, when m takes x, I get 0. For example, the matrix 1, 1, 2, 2, if I multiply it by the vector negative 1, 1, I will get 0, 0. So how does this relate to my structure? Usually I'm solving the equation that says k multiplied by u is equal to f. And what does this tell me? It tells me that there's a vector. The structure can move without external forces. If the structure can move, can have a displacement without external forces, therefore the structure is unstable. So all it finds is this matrix invertible or not? And the opposite argument holds. If the determinant is not equal to 0, m is not invertible, the vectors associated with m are linearly independent, and the only vector that m takes to 0 is the 0 vector. So m the only vector which when I multiply by m, I get the 0 vector. The only one is actually the 0 vector. And that makes m to be invertible. So if m is invertible, then the structure is stable. We are used to the transpose of a matrix as follows. M transpose, this is M. We're used to M transpose being M11, M21, M12, M22. This is basically saying M transpose Ij is equal to Mji. But there's an easier, I mean, it's not easier, there's a more, there is an abstract definition that helps that minimizes the use of components. And this abstract definition is if M is a matrix n by n, then M transpose is defined as the unique matrix satisfying for every x and y in Rn. When I take x dot my, it's the same as taking M transpose x dot y. There's another matrix. When I multiply it by x and take the dot product with y is equal to when I multiply x with the dot product of my. This matrix is actually the transpose of M. Now this abstract definition, this whenever you're trying to prove some of the arguments, it's easier to use this abstract definition. Also, if you're not using any components, because usually, but most of the cases we're using components, but if you're not utilizing components, if you're saying I live in R3, but I'm not utilizing any of E1, E2, or E3, then it's easier to utilize this definition. Inverse of a matrix. What does the inverse of a matrix mean? This is a vector x. When I multiply the vector x by matrix M, I get a vector y, which is equal to mx. If this matrix is invertible, therefore I have another matrix that I'm going to call M minus 1, which when I multiply M minus 1 by y, I will get x. So mx is equal to y. And when I multiply this matrix, which I call M minus 1, it's not really 1 over M, it's just the inverse of M. When I multiply M minus 1 by y, I get x, which means M minus 1 multiplied by M multiplied by x is equal to x, which means M minus 1m will also be equal to M minus 1, which is equal to the identity matrix. The identity matrix. Identity matrix takes a vector x and gives me the same vector x. I'm just going to write something here, just in case if you're not reading all the notes. If the linear operator from Rn to Rn is invertible, then the matrix associated with the linear operation is invertible, let's call it the matrix M. Therefore, there exists another matrix, it's also n by n, such that m minus 1 is equal to m minus 1 m is equal to the identity operation, or the identity matrix. The next topic that we want to talk about is the eigenvalues and the eigenvectors. Eigenvalues and eigenvectors. So, what is the eigenvalues and eigenvectors? Let's look at it in a graphical point of view. From a graphical point of view, the eigenvalue problem is the following. We know that for every x, there is another vector here. There is a linear operation m. There is another vector here, mx. Now this vector could be longer, could be shorter, could it be in the same direction, could be rotated, could be zero, it could be a lot of things. If it happens that I find a vector called P. When I multiply the matrix by that P, I get the same direction, but longer or shorter. If this is the case, then I call this vector the eigenvector of m, and I call the multiplier the eigenvalue of m. So if there is a vector, when I multiply m by this vector, I get the same direction, but maybe shorter or longer. That's an eigenvalue. That's an eigenvector of m, and the eigenvalue is that multiplier. Now, eigenvalues and eigenvectors appear, of course, you hear them all the time. They're very important because, especially for symmetric matrices, because symmetric matrices have, when you diagonalize them, and we're going to cover this, what you find on the diagonal are their eigenvalues. So let's just refresh or quickly see if you guys are still awake or not. The matrix I. What do you think? Does it have eigenvalues or eigenvectors or not? In fact, every vector in the space is an eigenvector of I. Because every vector, when you multiply it by I, it keeps its direction. Because every vector keeps its direction, then all the vectors are eigenvectors of I. For every vector in Rn, Ix is equal to x, therefore Ix is equal to 1 multiplied by x, therefore this is an eigenvalue. And x itself is an eigenvector. So all the vectors are eigenvectors of I. So, orthogonal matrices are, so we need to cover two things before the end of today. Orthogonal matrices and symmetric matrices. Orthogonal matrices are useful for the change of basis, and symmetric matrices are important because all the stiffness matrices all the stress matrix, the strain matrix, all these matrices are symmetric. So we really need to understand, instead of studying the stress on its own, the strain on its own, the stiffness matrix on its own, we need to study just a symmetric matrix, what are the properties of the symmetric matrix, and then apply all those properties to any of those matrices. So an orthogonal matrix is usually used for a rotation or a reflection. So what is an orthogonal matrix? An orthogonal matrix, I'm going to Q is orthogonal if